Hey, welcome to the Explainer. Today we're going to break down how computers talk to each other. And just so we're all on the same page, we are talking strictly about what happens inside an organization's own network. We're not getting into the whole internet today.
Okay, so let's kick things off with a question that really gets to the heart of it. Have you ever wondered, when you send a quick message to a colleague, someone just across the office, what's actually happening behind the scenes to make that work?
So here's what we've got on tap. First, we'll look at how computers are connected. Then we'll get into the rules of the road they follow. After that, we'll actually follow a message on its journey, check out the hardware that directs traffic, and wrap up with a really important security strategy. All right, let's dive right into our first section, connecting computers. And to do that, we've got to start with the absolute basics. What even is a network? At its heart, a network is really simple. It's just a bunch of devices connected so they can share stuff. The analogy that works best is a postal system. The network is the whole system, the mail trucks, the sorting centers, the mailboxes, that lets computers send and receive data, kind of like how we send letters and packages. And here's why this is so critical, especially if you're in risk or compliance. It's simple. You can't protect what you don't understand. Defining that network boundary, knowing exactly what's inside versus outside, is step one of any security review. Without that, you're basically leaving the doors and windows of your building wide open.
Okay, so we've got our computers connected, they're on the network, but how do they actually understand each other? How do they make sure the data one sends is readable by the other? Well, that brings us to our next piece of the puzzle, protocols. Protocols are basically just the rules of the road. If the network is the postal system, then protocols are the rules for addressing an envelope, right? We all agree on where the address goes, where the stamp goes, where the return address goes. It's that agreed upon format that makes the whole thing work. Without it, you just have chaos.
Now, from a risk perspective, this is a really big deal. Why? Because some protocols are secure. They encrypt the data, while others send it in plain text. Using an insecure protocol is literally like sending your company's secrets on a postcard. Anyone who's listening in can read it plain as day. That's a huge red flag for any auditor. Okay, now we're going to get into something really cool. See, all this communication, it doesn't just happen in one big step. It's actually a journey that happens in multiple stages, or what we call layers. And to understand this journey, we have a kind of map. It's called the OSI model. Think of this model as a 7-story building. Each floor has a different job. At the very bottom, layer 1, you have the physical stuff, the cables, the Wi-Fi signals. As you go up, you have layers that handle local addressing, then long-distance routing. Then you get layers that manage the connection itself and break the data into pieces. And at the very top, you have the layers that format the data and actually interact with the software you're using. The beauty is, each layer only has to worry about its own job.
So how does this all work together? The magic word is encapsulation. As data travels down through those 7 layers, each layer wraps it in its own little package, kind of like a Russian nesting doll. On the way out, a wrapper is added at each layer. And on the receiving end, each wrapper is removed as the data goes back up. Okay, let's make this concrete. Imagine you're sending a simple message in a chat app, "Are you available?" That message starts its life right here, at the top, layer 7. It's just plain text, exactly what you typed.
Then it gets handed down to layer 6, the presentation layer. And this is a super important step for security. Here, your message gets encrypted. It goes from, "Are you available?" to a bunch of unreadable gibberish. It's completely scrambled.
After it's encrypted, it keeps going down through layers that manage the connection and chop the data into smaller pieces. Then it hits layer 3, the network layer. This is where it gets its long-distance postal address, the IP address. Think of this as the full street address, city, and zip code for the computer it's trying to reach. And for the final step on the way out, it gets to layer 2, the data link layer. Here, it gets its MAC address. Now, if the IP address was the building's street address, the MAC address is like the specific apartment number. It's what's needed for that final local delivery right to the correct device's doorstep. So, why did we just walk through all that? Because it perfectly highlights the risk. Every single one of those layers is a potential point where someone could be listening in. If we hadn't encrypted that message back at layer 6, it would have been an open postcard for its entire journey. And trust me, for an auditor, finding sensitive data flying around unencrypted, that's a major, major problem. So we've got this whole layered journey for our data, which is pretty amazing. But what's the actual physical hardware that's doing all this work?
Let's talk about the guards and gates of the network. Okay, so there are three main players you need to know about. First, you have a switch. Its job is to connect devices that are on the same local network. It's the traffic cop for the neighborhood, using those layer 2 MAC addresses. Then you have a router. This connects different networks together, and it uses the long-distance layer 3 IP addresses. And finally, the firewall. This is your security guard, standing at the border and deciding what traffic is allowed in or out. And for anyone in an audit or compliance role, looking at firewall rules is just standard practice. The core idea should always be to block everything by default and only allow what is absolutely essential. We call this least privilege. A firewall with rules that are too wide open isn't just a security risk, it's a ticking time bomb for compliance.
All right, so now that we've got the equipment and we understand how the data travels, we can talk about one of the most powerful security strategies there is: the idea of building walls inside your network.
This strategy is called network segmentation. All it means is you're dividing your big network into smaller, isolated zones. The analogy of a postal facility is perfect here. You have the public lobby where anyone can go, then you have the staff-only sorting floor, and then you have a high-security room for valuable mail. You can't just walk between them. Access is tightly controlled.
And this is the payoff right here. In a flat network, where everything is connected to everything else, one compromised device can be a disaster. It can see and attack pretty much anything else on the network. But in a segmented network, that damage is contained. If one zone gets breached, the damage stays in that zone. It can't easily jump over to more important parts of the network.
So let's do a quick recap. Networks connect our devices, and protocols are the rules that let them talk. We have the 7-layer OSI model that maps out the communication journey, using that encapsulation trick to wrap the data. We've got our hardware, switches, routers, and firewalls, managing and protecting all that traffic. And finally, segmentation is that critical security control that limits the blast radius if something bad happens. So we'll leave you with this final thought to chew on. If your network really is like a building, how many unlocked doors have you left open? Understanding the blueprint is really the only way to know for sure.